Let's now look at the invariants in the complexity. These are the promises every operation must keep, and the running times they lead to. An invariant is a rule that must always be true. The left column states the rule. The right column tells you why it matters. Let's walk each one. First rule: 0 is less than or equal to size, and size is less than or equal to capacity. This matters because writing at an index at or above the capacity is a buffer overflow. Second rule: element I sits at data plus I because data has type pointer to int. Adding I already steps over whole elements. In bytes, that is the base address plus I times the size of one element. Do not multiply by the element size again. The whole big O of one get and set trick depends on this contiguous layout. Third rule: the live elements fill the indices from 0 up to size -1, with no gaps. A gap would break in-order scans and the meaning of size. Fourth rule: the indices from size up to capacity -1 are allocated but unused. That spare room is exactly what makes appends cheap. Fifth rule: after a resize, data names the new block only. The old block is freed. Any pointer still pointing into it now dangles, and using it is a bug. This table lists each operation, its time, and the reason you already saw. Let's read down the rows. Get and set at D of I are big O of 1. The address is base plus I times the size of one element. That is one computation and one access. A typical append is also big O of 1. It just writes into the spare slot at index size. An append that triggers a resize is big. O of n, it has to allocate a new block, copy all n elements, and free the old one. But the amortized append is back to big O of 1. The total copies over n append stay under 2n because we double the capacity each time. Insert in the middle is big. O of n, you must right shift up to n elements, and maybe grow the block as well. Delete in the middle is also big. O of n, you must left shift up to n elements to close the gap. So the dynamic array keeps the array's big O of 1 indexing, and it gains a big O of 1 amortized append. Its weak spot is the same as the plain array. Insert and delete in the middle are big O of n, because contiguity forces a shift.